All right, let's see. So let's minimize that.
So, Dr. Michaelson, we're supposed to edit the Excel spreadsheet on Teams, right?
No, you're not.
Right?
No,
Right?
I posted it. I post.
On Teams.
I posted it, and then 5 minutes after posting it, someone.
I thought I downloaded it on my phone. I really did.
If it makes you feel better, somebody in my other class did the same thing. And it was like 10 minutes after I posted it. I said,
I think you should have just left your grades on there.
no!
We're snooping.
Hold on. All right, is this thing going to load or not? Come on. Let's see. It would help if I plugged this in. See, this is what happens when I have a meeting like right before class. Like I get all flustered. Well, but I'm canceling class next Wednesday. Does that counteract? We haven't talked about that. Does that counteract the tally? Also, so that means we can have class on Wednesday.
Is homework the
So right when the mistake happens, we all just
These are rather one-sided provisions to mistake counters. Just saying. Just saying. All right, let's get started. Okay, so a couple of updates. Attendance is up to date. The at-home spreadsheet is on Teams. The bonus homework is on Teams. So if you do the survey and talk about how many mistakes I've had added to the mistake counter and say I'm the, all that, say that Alejandro is better, you can do that. Say whatever you, in all seriousness, in all seriousness, if there are areas that you think where the course should improve, I do take that pretty seriously. So if you do the survey, again, you can say I'm the worst professor ever. That's fine. I just want you to do it. But if you upload proof that you've done it, I give you another 10 points on top of your homework average. Let's talk about schedule because we are winding down to the end. Today we are going to talk about some more LTB, and we're specifically going to talk about design, and I'm going to show you the craziest, what looks like the craziest design aid ever. It's actually incredibly helpful, and it is a lot easier to use than it looks. But it is very seminal. There's a page of it in the FE reference manual. What we're going to do today is continue our discussion of analysis, though, and talk about the procedure for design. What we're going to do for actual design is we're going to have 2 days focused on discretely braced beam design. And if you notice, there are two sort of types of problems that we deal with. What I would call low CB designs and high CB designs. That doesn't make a lot of sense now. It will later. Trust me. You'll understand what I mean by low versus high CB values. One of the things that we're going to discuss on Friday, and I have been purposefully putting it off, is shear. We haven't actually talked about how to compute the shear capacity. We just said, oh, we'll get to it. Well, I'm going to talk about it on Friday. And to be honest, again, in building design, not that big of a deal. And that is completely antithetical, for example, to concrete design, where you spend a lot of time talking about shear. And it's also different than bridgeland. If we were talking about steel plate girder design in bridgeland, we would spend a lot more time on shear than we do in here. But we just don't. On Monday, our final topic in the class is local buckling. And this applies to columns and beams. We kind of just haven't talked about it yet. And it's kind of easier to do it at the end. We've been assuming this whole time that the sections that we investigate, that this isn't a problem. But it could be. So I want to talk about how you would address it. And so I could throw another topic in on Wednesday, but I'm actually not going to do that. I have an engagement on that Wednesday anyway, so I would have to pre-record a lecture, but we're kind of done. So I'm just going to cancel class on Wednesday, and Friday we'll come and do our exam review. Here are the homework due dates. I am going to go ahead and make this local buckling assignment due on Wednesday. There's no reason not to, so that I can give you the solution on Friday, and we are done after your exam with CE 414. Sound good? Let's talk about LTB. Now, this is the be-all, end-all for LTB. This is our flow chart, which tells us that we have 3 zones of capacity for a beam that is a function of its unbraced length. The longer the unbraced length, as we see here in our model, the longer the unbraced length, possibly lower the capacity. And I say possibly because if we ignore the effects of CB, well, then that's true. We either have a constant MP capacity, we have a linear fit between MP and MR, or we have a hyperbola based on our buckling solution. But CB serves to augment our capacity up to a point. I don't care what CB does, your capacity is limited to MP. So with that, we did one example. We did one example last time looking at what I would call a pretty simple problem. Let's talk about the example we did last time. The example that we did last time in class, what was it? It was a simply supported beam, uniformly distributed load. Now, how many unbraced segments were on that beam? Well, no, there were 2, but hold on, let's talk about that. So there were 2 unbraced segments for that beam, right? It was a simply supported beam, uniformly distributed load, and there were braces at ends and at midspan. So there was a segment on the left side and a segment on the right side, right? But we only considered one. Why? Well, both segments had the same length, both segments had the same max moment, both segments had the same CB, right? So they performed the same way. With me so far? Now I want to talk about this problem, just to make sure that you're paying attention. What about a beam like this? So each segment might have a different LB value. Each segment has a different CB value. Each segment has a different Mmax. So I propose that each of these segments is going to have a different capacity, different phi Mn. Okay? So the way that you would handle this as an engineer is you would look at all of them. You would compute the Mmax for this segment, compare it to its phi Mn, the Mmax here, compare it to its phi Mn, and the Mmax here, compare it to this phi Mn. And the segment that governs is the one that has the largest efficiency, or the largest performance ratio, as we looked in our last example. Now for shears, you just use the maximum shear overall, and for deflections, just use the maximum deflection across the entire beam. I just want you to know that the problem we did last time was simple because both segments were the same, and to be honest, we try and exploit symmetry whenever we can in real-life applications. But it's possible that you don't have symmetry, in which case, take the one that has the largest efficiency. And the one that has the largest efficiency might not be the one that has the largest moment on it. In other words, you might plot the shear and moment diagram, and you might have a segment that has a lower moment than another, but the efficiency is higher because of the CB and the capacity and whatnot. Does that make sense? All right, I want to look at this problem. This is the determining the flexural capacity of a W14 by 61. This is going to be pretty straightforward. I'm giving you some of the values that you need for computation, but I want to make a point. Okay, and before we open up the calculations here, I'll open up the notebook, but I want to make a point. Ooh, sorry. Let me go to the notebook here so that you all can see this. I made a note here for this problem that a W14 by 61 is not one of the bold rows in Table 3.2. It's not. There is a reason why we're looking at a section that's not a bold row. That doesn't make a lot of sense now. It will later. Okay? But suffice it to say that your most economical design for a given problem might not be a bold row in Table 3-2. So just be forewarned that that can happen. Okay? Everybody good so far? Now, what I want somebody to do is find the W14 by 61 and help me out with something. What the? I don't know what happened there. I want you to tell me what LP and LR are for a W14 by 61. And so it is in Table 3-2. I'm not saying it's not. It's there. It's just not one of the bold rows. All right. I want to make sure that everybody can find it, because everybody brought their AISC 15th edition steel construction manual with them, right? You're giving me this look, you know. Let's talk about tally marks. All right.
We can keep class today.
Okay. Now, why did I ask you to write LP and LR? Because I'm trying to determine what zone this beam is in. What zone is it in? Well, how do we determine that? We look at this, right? And so what zone are we in for this beam? Well, hold on. Let's make sure we all know what we're doing here. Hold on. Zone 3. All right, so here's what we're doing. Here, I'll screen clip this so we have it in our notes. So here's our model for capacity, right? And we determine what zone we're in by comparing LP and LR to our unbraced length. And we're in zone 3 because our unbraced length was given as 30 feet, and LR was given as what, 27.8 feet? Is that right? So that's why we're in zone 3. Okay, with me so far? I want to stop, make sure that we're clear on why we're in zone 3. Because there's a couple people that are giving me a look like, what are you doing? Everybody good? Okay, now, all right, let's look at this equation. This is the first thing that we have to compute. It looks nasty. It's really not. It's just a lot of plug and chug, okay? So let's look at the values that we need and what values we're missing. Do we know CB? Were we given CB at the beginning of the problem? It's 1.5. I think we've seen this number before. It's like 3.14 something, right? Pi. We know E. LB is our unbraced length, which is 30 feet, okay? We need to be careful with the units here, okay? Because RTS is not going to be in feet. It's going to be in inches. We don't have RTS, but that's something we can look up, okay? All right, 1 plus 0.078. Okay, now let's look here. We have JC over SXH naught. We need to look up all of these except for C because we're given C is 1. C is always 1 for I shapes. When we're looking at channels, there's a modification there. So we've got J, SXH naught, and then we have RTS. Okay, so those are the quantities that we're going to need to look this up, or to compute this. So for a W14 by 61, and we can go back to table 1-1, okay, we're going to need some values, okay. Specifically, what we're going to need is the following. We're going to need, skip ahead a little bit. We're going to need SX. We're going to need RTS. We're going to need H naught. And we're going to need J. Those are the values that we're going to need. So for a depth 14 by 61, what are these values? Unfortunately, with zone 3, there's no, like we kind of just have to work our way through it. Like there's no real handy shortcut. So what's for the, what's SX for a W14 by 61? 92.1. Wait, what? All right, so 92.1 cubic inches. RTS. H naught. Now H naught is just a little shy of the depth because it's the distance from the center of the flange to the center of the flange. So it's just a tad shy of the depth. There we go. And then J, I can do that one for you. It's 2.19 inches to the fourth. Okay? Now note, we are going to need LB, which is 30 feet, but we need to go ahead and convert that to inches right now. We need to do that because we're going to take LB over this, and we have to have consistent units to take LB over RTS. Okay, so, and I think this probably takes the record for the longest equation in this class that you actually have to use. So, therefore, FCR is CB pi squared E over LB over RTS, and that quantity squared, that's like a slenderness squared, and then 1 plus 0.078, we have a fraction, then we have our slenderness squared, and we take the square root of all of that. Again, I know it's kind of nasty, but that's our expression. Fortunately, though, everything that goes into this expression is very plug and chug. So I'm going to raise this up a little bit. So we have 1.5. We were given CB. We've got pi squared. We've got 29,000 KSI. Now, what's interesting is I actually want you to sort of pay attention to E in this equation. There's a reason I want you to pay attention to it, and you'll see why here in a bit. So 7, 8. Don't forget to square your slenderness. This one I kind of think we all need to do. This is a long equation. It is one that you could very possibly use in this class and on this exam. I really think we all kind of need to break out the Casio FX115 ES Plus or similar scientific calculator and chug this one out. Now, while you all are chugging it out, one question that I would ask you is, what are the units? What are the answer? What units is the answer going to be in? Now, if we look inside the square root, what do we have? Inches over inches. They cancel. What about this bracket? Inches to the fourth over inches to the fourth. They cancel. Down here, inches over inches cancel. Remember how I said to pay attention to E? E is in KSI. That's what the answer's in. So it's a lot of unitless stuff, and then we get to KSI.
I ran out of digits.
You ran out of digits?
I won't let you put it anywhere.
So you might need to do the stuff in the square root first.
I got 46.7.
Okay, 46. Is that what you got? So you might need to do the square root first. Like, do this, take the square root, then do this fraction that times that.
Yeah, mine fit on my screen. Mine looks really cool. Yours is just junk. I got a junk calculator.
I'm sorry. Maybe like refresh the memory.
Yes, it's like an S4.
That's it. I think it's a minus right now. Like, burn. All right. Did everybody say 46.78? Everybody good on that? Okay. I would make sure that you are comfortable with that. Okay? All right. Now, if you are with that, let's let's do some calcs. Okay? Phi B, FCR, SX. Now everybody pay attention. Phi B, phi is our resistance factor, which is 0.9, 46.78 KSI. What was SX again? 92.1. What are the units going to be as a result of this computation? We're computing a moment. No, that's KSI. That's cubic inches. It's going to be in inch kips. If I want it in foot kips, if I want the answer in foot kips, I need to throw my unit conversion in there. So that's what I say. I want everybody to pay attention. You got to do that, okay? So what do we get for this? 323.1 foot kip. Do I have a second on that? All right. Now we always compare that against that. What is phi MP for a W14 by 61? It's almost like we need to go back to table 3-2 and look up phi MP. You're in the wrong table. Table 3-2.
Oh.
Yeah, you got to that. This is the one that's computed for us. 383. Okay, is everybody able to find that? So what I'm getting at is phi mn is the minimum of phi b FCR SX or phi MP. And what is that? It's 323.1 foot kips. All right. I'm going to take a step back, make sure that we're all clear with what we did here. I mean, ultimately, I know this formula was kind of nasty, but it is pretty methodical. It is pretty procedural, right? We're just going to our flow chart and we're saying, okay, here's our flow chart. We're in zone 3, plug and chug. And so you can see what I did here. Phi mn is the minimum of that or that. You just got to make sure here that you're careful with your units. With me so far? Yes.
I just have one question about how it says JC.
Yes.
Where does the C come from? It was 1 in this case, but...
So that's a great question. So C is an adjustment for if we're not dealing with an I-beam. If we are dealing with an I-beam, there's a pretty plug and chug expression. If you open your manual and you turn to chapter F, it's in, hold on, give me a sec. So it's 16.1, so we're back in the spec. 16.1-48. It's on the bottom left. So chapter F is the chapter that has all these expressions for LP and LR and all that stuff. And if you look at the bottom, you'll see where it is. Yes, that's a great question. So the short answer to that is yes. Here's the longer answer. These equations kind of break down when you're going outside that. If you don't believe me, just look at how chapter F is organized in general. Like if you go to the beginning of chapter F, there are sections for angles, sections for HSS, sections for this. Bending's hard, right? And so sometimes these nice, pretty expressions don't work for angles or for other shapes. And when they don't, That's what this is for. There are different expressions that do work, right? Now, the reason that I'm only showing you this is because this is steel design. 90% of all elements that we bend are I-beams, right? So that's why we're using this, right? Does that make sense? That's a great question. So that happens. You know, one of the nice things about the manual, though, is look at that page on the right at the beginning of the chapter. So it's 16.1 dash 45. This is a wonderful guide, right? Because it says, okay, if you're dealing with an angle, you need to go to section F9, right? Or F10, or, you know, what if you're dealing with a round tube? You go to F8, and it will list similar expressions for you. Does that make sense? All right, any questions? All right, I want your eyeballs up here for what we're about to do. Okay, eyeballs up here. Let's talk about designing. Now, design is about selecting shapes to adequately resist loads. Now, I want to go back to column land and make sure that everybody remembers this. Okay, so we put KL over R here, we put F critical here, and we had this curve that kind of looks something like that, right? We had this dividing line here that was 4.71 square root of E over Fy. And we had this was 0.658 raised to the Fy over Fe times Fy, and this was 0.877 Fe, right? And what was Fe, by the way? Fe was pi squared E over KL over, I don't know what happened there, KL over R squared. I think it's because I hit the cord. I think that's what I did. Sorry about that. All right, this was our column curve, our AISC column capacity curve. So if I wanted to plot the actual curve for a given column, how many properties do I need for that column? And to give you an analogy, we just did an LTB problem where we needed SX, we needed H0, we needed RTS, we needed J. How many properties do you need for a column? You just need one, right? And that's R, right? You can plot the whole curve with just R, right? With me so far? The problem is when we look at the beam curves, it's just nastier, right? There's just a lot more, right? We need RTSs and SXs and ZX and this and that. There's just too many parameters that go into the construction of a given LTB curve for a single beam. Do you remember when we first started looking at this curve and I showed you that little spreadsheet that worked for a W24 by 76? Y'all remember that? And I was changing the CB values, and you saw what the curve did? Well, if I said, no, this isn't a W24 by 76, let's change it. Let's do a W30 by 90. Completely different curve, right? There's just too many parameters that go into it. Different LPs, different LRs, etc. There's too many parameters in one curve, so how do we design? Well, we need some design aid. And unfortunately, we cannot use a single curve because each beam has its own curve, right? So what do? We plot them all, okay? Now, I can already see the looks on some of your faces, and you go, what? This is crazy. This is a lot easier than it seems, and I'll show you. Okay, the way the manual figures this out, and the way that we have figured this out in the steel industry, is if every beam has its own curve, we just plot them all, okay? And so this is table 3-10. This is the LTB design aid. This is a tabbable guide, okay? And all it is just the LTB curve plotted on top of one another, okay? Now, a couple things. I want everybody to turn to this. I want everybody to open this and have their their AISE 15th edition steel construction manuals that they all brought with them to open to table 3-10 because I want you to kind of see this. All right? Now, let's go back to this. So what do we have? We have LB plotted on the x-axis. We have phi-mn plotted on the y. Unbraced length plotted on the x-axis. Phi-mn plotted on the y. And you can kind of see what's going on because here's that, then it goes down, and then it's going to turn into the hyperbola a little later. Now, a couple things to pay attention to is this right here. This little top corner. This is really important. This top corner says that this guide only works if Fy is 50 KSI and Cb is what? 1. Obviously, we know Cb doesn't always equal 1, so we got to work our way around that. We got to figure out how to deal with that. We will. Don't worry. Now, eyes up here. I got some animations, some nifty little graphics that are going to show up. Here's how this table works. First, we have to divide out the effects of CB. Okay, so what that means is we do some structural analysis. So we have a segment, it's got a maximum moment, it has a CB value. We go into this table with MU divided by CB. So we divide out the effects of CB so that we're entering the table sort of kind of assuming CB equals 1. And so what we do is we look for the point in the table where on the x-axis we have our unbraced length, and on the y-axis we have our moment. In this case, our factored moment on the beam divided by CB. And we look up and to the right for the first shape that's a solid line. So watch this. Let's do a quick example. Okay, so let's say that LB is 28 feet, and let's say that MU over CB is this value. So everybody watch this. So what you're going to do, boop, find that point. You missed the boop, right? Let me do it again. Boop, right? You find that point, okay? Now there's that point. That's the point that corresponds to the problem I'm doing. So keep watching, okay? Now I propose that everything in that blue shaded region is a valid design, okay? Or a valid choice. Why? Why that region? Well, that region corresponds to beams that either have a longer unbraced length or can hold up more moment, okay? And so what I'm going to do is I'm going to look up to the right and I'm going to find the first solid line shape. And that shape is a W27 by 146, and that's what I'm going to try, okay? Now, there's probably a natural question. Why are some lines dotted and some lines solid? Well, why in table 3-2 were some lines normal and some lines bolded? Why were those top rows bolded? They were the most economical shape within a given region. The solid line curves are the most economical regions the most economical shapes within that region. Okay? The thing is, because of the nature of the curve, these solid shapes might not necessarily correspond to a bolded row in table 3-2. That's why the example we just did today was not one of the bold rows in table 3-2. Does that make sense? Okay. Now, you all have manuals because everybody brought their AISE 15th edition steel construction manual with them, obviously. We're going to make sure that we're comfortable with this. So I want everybody to help me out. I want you to find the solid line section corresponding to an unbraced length of 14 feet and a moment of 2150 foot kips. Right now. I have spare AISE 15th edition steel construction manuals for anybody that did not bring one. And I want to make sure we're all comfortable with this.
W36 by 182.
All right, let's see. I don't remember, so let's see. All right, so I'm getting a different one. Okay. All right, so First off, let's agree what page are we on? 3-99, okay? So, hold on. Let's see. All right, let's try something. Let's see if this works. All right. 3-99, you said? Hold on. Okay. So, let's see. We're looking at this. So you're on this page right here. So let's see if we can snip this and put this into our notebook. I'm telling you, this does not like numbers. Yeah, I think I'm getting rid of this. I'm getting rid of this notebook or this little keyboard after the semester's over. Okay, so here's the table that everybody's looking at, and we're going to, what was it, LB of 14 feet? So that's this line right here. What was the moment again? 2150. So 12 kips, that's something about like that. So we're on, that's the point, right? That's the one that we're using, right? And so anything here, anything in this upper region will work. So I go up and to the right, and that's the first shape that I pick is this one. And so I look up, and I'm getting this label right here. This is the, that's the label. So try a W40 by 167. And I'm just curious. Okay, that is a bold row. That is a bold row. Sometimes it is, sometimes it isn't. It just depends. Okay? Does that make sense? So this is just some quick practice with table 310. Now, if you remember, I said that there were going to be 2 days of beam design examples, and I said that the 2 cases are what I'm calling low CB values and what I'm calling high CB values. I remember that. So the difference is that when you have a really, really high CB value, it can cause you to have to go back to this table quite a bit. There's a lot of page flipping with high CB values as opposed to low CB values. And I don't want to get too far down the rabbit hole with that because I kind of want to make sure that we understand the process. All right. So everybody with me so far? Does everybody understand what we did today? Now, my goal for today was to finish the LTB examples, the analysis examples, right? So we've actually done 2 examples for analyzing a beam, right? We did one that was in zone 2, one that was in zone 3, right? Your homework assignment due Wednesday is an analysis assignment. Starting Wednesday, we're going to do design. And so we're not using it. This is not a requirement for your homework due Wednesday. I want this part to kind of seep in about how to use this. I don't want you to be scared about this. It's not scary. It's actually really useful and really simple to use. It looks like a nightmare, but it really isn't, okay? With me so far? All right, one final thing. Again, if you haven't indicated your preferred Tuesday or Wednesday time slot on the final, do so. Again, I had a typo on the days. My apologies. But again, the idea is you're either taking the final Tuesday of finals week or Wednesday of finals week. So just let me know. All right. And there are some people that weren't in class today. I will send emails out, but I will put this question on the next attendance sheet. But at some point, I kind of need to hear from everybody what they want to do. So they kind of need to come to class. All right. That's all I got. I will see you all on Wednesday. That's a possibility.